This is another video about differentiable functions. Going to focus on when you've got a strictly monotone function that's continuous and has a derivative, what can you say about the derivative of the inverse function? So there's a theorem for that. So if you've got an interval I, that's a subset of the real numbers, that's an interval, and you've got a function f whose domain is I, and let's say that that function is strictly monotone and continuous. So then, well, this part tells me that this function f has an inverse, and if I assume that f's continuous, then I know the inverse will be continuous as well. So why don't we let j be just a shorthand notation for the range of that function f, which of course would be the domain of f inverse. And instead of f inverse, it's a lot of baggage. I'm just going to refer to it as g. So g will be the inverse of f. And so g is a function that goes from j to the real numbers, and again, we know that g is also strictly monotone. So remember, like if f was increasing, then g is increasing as well, and if f's decreasing, then so is g. And also what I was just saying is that if f's continuous, well then g should be continuous as well. So here is the new thing. If f's differentiable at some point c in its domain, and if the derivative of f there is non-zero, then we can calculate the derivative of g at the corresponding point f of c, which for shorthand we'll just call d. And then what is the formula? The formula for the derivative of g at the point d, which again is the output of this point c that I know about, it is just 1 over the derivative of f at c. And maybe another notation for that, just because I know, okay, d is f of c here, I'll just swap that in. G of d would be what c is, if you think about this formula here. And why is that kind of cool? And I'll show you this in a minute too. We'll prove this first and then we'll do some examples. But this formula was always kind of cool to me because I don't really even need to know a formula for what g looks like, let alone the derivative of g, but I could still calculate values of the derivative of that function. Kind of cool, just based on information that I know about f. And I'll try to explain a little bit more what I mean by that when we do some examples in a bit. What's the proof of this look like? So we're going to try and prove that this function g is differentiable at this point, f of c. And so to do that, we'll use Caratheodory's theorem. So by Caratheodory's theorem, there exists some function phi whose domain is the same domain as f, so this interval I, and I know that phi is continuous at c. And remember, this phi satisfies some kind of a functional equation where phi satisfies this equation down here, which kind of looks like maybe the point slope form of a line, where like these are the y values, this is the difference in the x values, and I know that's supposed to be the slope. So phi satisfies that equation for all x in the interval I. And then finally, phi evaluated at c is actually just the derivative at c. And so maybe remember, phi is sort of like a function that calculates the slope of the secant line between 2 points on the graph of f. And the idea is, well, as those 2 points on the secant line get closer and closer together, maybe closer and closer to c, I should be more specific, well then phi ought to just be the slope of the tangent line there. Remember, like as your points, maybe I should draw you a picture. So maybe if I've got my graph here, let's say here's x and here's c. As I'm thinking about making the line that connects these two dots, as I drag x closer and closer to c, well then that new line would really just be like the tangent line to the graph at that point, which I guess maybe looks like that. So remember, phi is calculating the slope of like each one of those lines. Okay, cool. I talked about that too in a previous video. I probably spent way more time than I needed to telling you about that right now. But let me see. So by hypothesis, what did I assume? Well, I assumed that the derivative, that's not a highlighter, is it? I assumed that the derivative of f at c is non-zero. And so in that case, well, if phi of c is f prime of c, then phi of c is not zero either. So what does that allow me to say? Well, since phi is continuous, I know that that means there should be some little neighborhood around c where phi is just non-zero. So like phi can't be just non-zero at one point. There should be some whole neighborhood where phi is non-zero. And so what can I say? There exists some delta such that phi of x is non-zero for all inputs that are in this interval here, which is the domain of f intersected with, again, this little interval around c. And what I'm going to do is I'm going to let u, maybe a shorthand, I'm saying call this part v. So then we'll say u is just the image of that, or send all those points through f. And I'll draw you a picture over here. So what I'm trying to say is maybe the graph of phi looks something like that in white. So I'm saying that you should be able to find some little interval in blue around c. so that the graph of phi never dips below the x-axis. And then what I'm saying is that this u is just the output of all the points in blue when you plug them into f. Okay. And so what else can we say? What do I know about f and g? They're inverses of each other. So f of g of y should just give you back y for every y that's in u. So what we're going to do is, okay, so this, if I think about y minus d, by this logic, that's the same thing as f of g of y. And remember, d is f of c. So that's up there in that blue color. So d is really f of c. But then this looks like the difference between maybe two outputs, two y values on the graph of f. By Caratheodory's theorem, I know that should be phi of g of y times g of y minus g of d. Now what we're going to do is we are going to, if I know that phi is non-zero as long as the input of phi is within this nice window here, well, the whole point of this is that, well, y is in this window here, therefore g of y should go back to the blue. So g of y should live in that nice interval that guarantees that phi is non-zero there. So what does that enable me to do? It enables us to divide by phi of g of y, and we're going to divide it over to either one of these sides. Actually, I think this side's a little more useful for me since I see I've got y's and d's over here. So that's what we're going to do in the next step. So because phi of g of y is non-zero, since y lives in u, I get that 1 over phi of g of y times 1 y minus d. Remember, all I did was divided this just over to this side, and I'm going to write it as just multiplication by 1 over that instead of divided by. But then that would be equal to, what do you have left on this side? You just have g of y minus g of d. So again, that's this guy right here. And why is that cool? Well, because that looks kind of like Caratheodory's theorem. I've got this function, phi composed with g. That's the composition of continuous functions, therefore it's continuous. And it's continuous at this point d. And it looks like this function, actually I should call that, oops, I made a typo, didn't I? 1 over, right? I'm looking at this one here. So that function's continuous. And it looks like it satisfies kind of a similar functional equation where it looks like it's trying to serve as like the slope of the line that connects the points on the graph of g, you know, y comma g of y, d comma g of d. And so I can apply Caratheodory's theorem to this in order to conclude that g prime of d exists. And the formula for g prime of d should be the same thing as that formula that I had up here. Right, it should just be this special function from Caratheodory's theorem. In my case, again, it should be 1 over phi of g. So 1 over phi of g of d, which is just, again, 1 over f prime of c. So kind of a long proof, but again, it kind of emphasizes the importance of Caratheodory's theorem, gives us a nice way to think about the derivative and maybe a nice and useful way to prove some other powerful results. So let's actually see like how do you use this. So let's let f be this function, x to the 5th plus 4x plus 3. F's differentiable for all real numbers, and it's strictly increasing. I see the derivative is 5x to the 4th plus 4, and I see that that's non-zero, right? This thing only has complex solutions, so it's non-zero as far as the real numbers are concerned. And so therefore, I can tell you that the inverse of f should be a differentiable function. Now, I think just by like thinking about college algebra methods, that'd probably be pretty hard to figure out what the inverse of that function is. What's a formula for it? But nonetheless, I can still tell you some information about it. So what I can do is I can kind of calculate one by one, maybe what are the derivatives, what are the values of g prime. So let me show you how I do that for a specific value as an example. So let's say c is equal to 1. So if c is equal to 1, remember c is in the domain of f, so we'll plug 1 into f, and so I'll plug in 1 to these x's up here. So that would be 1 plus 4 plus 3. I think you get 8. So what does that tell me then? That tells me that g of 8 should spit back out 1, right, since g is the inverse of f. And so what does the above result say then? The above result should tell me what the derivative at g, what g prime of 8 actually is. So, and again, that is how I would think about this formula. I would use this, I'm thinking here, g prime of 8 should be equal to 1 over f prime of 1. So again, my d here is 8 and my c is 1. So g prime of 8 should be 1 over f prime of 1, which is 1 over 5 plus 4, right? I have the derivative of f right here, and I see that it's 1/9. So what I was trying to say in the beginning of the video, and nowhere in here did I tell you what g looked like or what g prime looked like. Nonetheless, I can tell you that the derivative of g at 8 is 1/9. Or if you gave me, say, any x value, I could do something similar as well. I could always tell you about information about the derivative of g, just based on information I know about f, which is kind of cool. Give you one more here. If I look at sine of x, but I restrict its domain to maybe between minus pi over 2 and pi over 2, then it's strictly monotone, increasing function, and it's differentiable. And the range of that would be minus 1 to 1. And I know the derivative is cosine of x, and I know at least I could say cosine is non-zero as long as I take the endpoints away in my interval. So on this open interval from minus pi over 2 to pi over 2. So then the inverse, which I'll denote by arcsine, maybe you've seen it before, it should be differentiable on its domain, which would be, well, the range here. But remember, if I'm talking about differentiable, I had to use parentheses here. So I'm going to use parentheses on the minus 1 to 1, right? Since sine of pi over 2 gives me the minus 1, but I'm saying I can't think about sine of pi over 2 because the derivative is 0 there, so I want to delete those points. Anyway, so let's talk about how do you figure out maybe a formula for the derivative of arcsine would be. So we'll use this nice idea here that y equals sine of x is equivalent to saying arcsine of y is equal to x. So let's say we wanted to find the derivative of arcsine of y. Well, what we could do is we could use our formula from the theorem that we proved, which says it should be just 1 over the derivative of sine of x. And I can do that. That's 1 over cosine of x. And what I ultimately want to do is, just how I wrote this, well, I guess I'd like to get y in the picture here. So what is cosine of x? So remember, if cosine squared plus the Pythagorean identity, cosine squared x plus sine squared x equals 1. If you solve that thing for cosine, you'd see that cosine of x is 1 minus sine squared of x in the square root. And so we have that. And then the last thing that we'll do is, as you see, the whole point of my color, that kind of rosish color, is that sine of x is y. So sine squared x is the same thing as y squared. So altogether, if I kind of recap here, I'll probably remind you of a derivative formula you may have seen before. It is that we've just showed that if I change also back to having x as like the independent variable, so this is kind of just a bunch of work to satisfy or to prove more or less the following definition. The derivative of arcsine of x should be 1 over 1 minus x squared in a square root. And that should hold for all x in minus 1 to 1. So again, when I'm using x's here, I'm kind of leaving the setting where I was using x's versus y's above. I'm just saying this is like a new derivative formula in general down here. Great.